Mohan, now it is live. Okay, okay, thank you, madam.
So that is all set from my side also. I have started recording in my computer. So I think you can start as formalities, please.
Yeah, very good day to all the participants. So on behalf of South Asian Meteorological Association and SRM Institute of Science and Technology, I welcome all the participants and panelists for today's talk. So today we are going to have a 12th talk of this lecture series. So as you are aware that we have 16 lectures of this lecture series, and we are in the third module, that is on the atmospheric radiation. So in the third module, we have reached the fourth lecture. So this is 12th lecture of the 16th week lectures. So today's lecture will be on the radiative transfer equations. The speaker is Dr. B. Mukhopadhyay. So on this occasion, I also welcome Dr. Professor A.V.M. Ajit Tyagi, the President of South Asian Meteorological Association, Dr. Mohan Kumar Das, Joint Secretary, South Asian Meteorological Association, and Dr. Rohini Bhavar, she is Assistant Professor, University of Pune, and Dr. B. Mukhopadhyay, IMD, Pune. So with this, I will hand over the session to Dr. B. Mukhopadhyay, sir, for delivering the talk. Over to you, sir.
Thank you. Thank you so much, Dr. Lakshmi Kumar. And greetings to all the panelists, esteemed panelists, and as well as all the guests who have joined in today. This has been a four-day lecture, the 4-week lecture, so to say, and I have been completely engrossed in it, and it has been so interesting for me. I hope from the other side also, those who are listening would find it equally interesting. In fact, the whole fact that SAMA is kind enough to arrange these lectures, that has really opened up wonderful opportunities. And I come to the final lecture of this 4-lecture series on radiation. And if I may go over to the slides. So this part 4, I'll be talking about transmission through the atmosphere. Now, when I talk of transmission through the atmosphere, it's kind of summing up what we have already done. We have seen how emission can be quantified, and as the radiation passes through a certain medium, how absorption and scattering play their part. So essentially, these 3 aspects that go into the radiative transfer process have been already discussed. All we need to do is to put it in one framework of an equation, and probably revisit the problem in terms of a few examples that we can pick up from the real life. So that being the purpose of this, I would also like to end this lecture with a few slides on observational aspects, because that is something which really does not come within the first 4, the way the lectures have been divided. But I have a feeling that for most people who want to apply atmospheric radiation to real life problems, a little bit about the instrumentation and their capabilities, very little of course, would not be out of place. So I have just inserted 4 slides at the very end. Having said that, let me now just take a little bit of a revision. And if you look at this, just 1 second, please. Yeah. We have come across these relationships, and they are related to the attenuation of radiation, and N and I are the usual terms used for radiance and irradiance, that is intensity per unit area of emission per unit solid angle, that is radiance. Now, this is This equation we have done in details. So all we need to recall is this, the right-hand side is an expression, an explicit expression for the absorbance. And absorbance is the absorptive power, so to say, the rate at which the fraction of energy that is attenuated by the passage through the medium. And here it's very important to recall that obviously this S is a geometric path, and we need to correct this in the real atmosphere for the refraction that is taking place through the medium. It is not just the geometric path. The geometric path is subject to refractive curvatures. So this is when we do some measurements at the very end, that will become a little more clear. So this is the path, all right, but the actual path after refraction through the atmosphere. And obviously the local density is a function of this location S. And this, as I told you, is a property of the molecules that constitute, or the components that constitute the medium. Now, please remember this, that this K has got the unit of area per mass. So if you're dealing with 1 unit of mass, then it is something like an area. And equivalent, sometimes it is called cross-section also. So you can talk of an absorption cross-section, or you can talk of a scattering cross-section. In a general way, you can use this. So when you talk of this, the optical path, this is mass per unit area. In other words, this is actually the number of interactive elements that are encountered, so to say, by the photons as they pass through. And constituted out of this is the optical depth, which is a product of all three integrated for a finite length L. And this is called the optical depth. And the intensity of radiation, or the radiance, falls off as e to the power minus of optical depth, which is a combined effect of the molecular properties, the densities, and the length of travel. The last unit, the term that we have used, this is a very general term, and it has got per unit length, unit of per unit length. This is called the volume absorption coefficient for 1 square, for 1 unit area of the cross section of the medium through which it is passing. And that is the product of these two. Now, this term beta is used not only for absorption, but also for scattering. And you can easily sum up the two, absorption component and the scattering component, and you can define one value called the volume attenuation coefficient. But when we find out fluxes, there is a different approach, because this is the total flux in a hemisphere. This relates to the total flux in the hemisphere. If you recall that slide on scattering, you will find that this was found out by integrating gamma, which is nothing but a function which tells you in a particular direction how much of light energy will be scattered. That function gamma has to be integrated for all solid angles. And you can do it for the forward half plane and the backward half plane. So you can have the flux moving forward and the flux, which is also known as the backscatter or the reflection. You can give it any term. So that will be in the second, that will be in the backward direction when you integrate it with respect to solid angle. So with this little bit of a recapitulation, let me now go to . some very simple concepts. Well, this is a little trivial, but nevertheless, to recall this may not be a bad idea. That is, there are two bodies in an enclosure. Okay, one is a black body and the other is a general body. It is not a black body, so to say. And it is maintained a certain temperature. So after some time, when it will equilibrate, all of these bodies will attain that particular temperature. So that is when it stabilizes. And at that point of time, there will be radiation given and the radiation absorbed. Now we just want to know the relationship between what is emitted and what is absorbed. In other words, you can very well understand we are hinting at the Kirchhoff's law of radiation. Now, very simple, let E be the emissive power of A, of this body, which is not a black body, and A be the coefficient of absorption. That means if multiplied A with the area, and what you get is the total amount of absorbed energy. Now, similarly, for the black body, it is EB, is the emissive power of the black body. The other thing is that the Q is the amount of radiant energy incident per unit area of each of these bodies. Now, this is an enclosure at thermal equilibrium. So Q will be the same for both these bodies. Now, this is something which is pretty obvious. Now, what it leads to is when the temperature remains constant after it has come to equilibrium, the energy absorbed by both the bodies is equal to the energy emitted by both the bodies. And here, for one of them, it is A into Q, because that's absorbance by definition. And for the black body, it is obviously equal to Q, because the black body absorbs everything, emits everything. Okay. Now, a very simple relationship comes from this, and that gives you the relationship between the absorbing power and the emission of the body. And what is that? E by EB. That is equal to A. Now, what is E by EB? By definition, is known as the emissivity or the coefficient of emission. That means compared to a black body, what is the emissive power of this particular body? This ratio is known as emissivity. Now, therefore, what happens is that emissivity is the same as absorbance or the power of absorption. This is known as the Kirchhoff's law. So if it has to radiate well, it has to absorb well. Otherwise, it cannot radiate. That's a given conclusion. This is exactly what it means. Now, whenever we talk of emissivity, we can replace it by the explicit use of this word absorbance. Just let's go back a little bit. Let's go back a little bit. What did you notice here? The entire right-hand side is nothing but A, isn't it? The absorptance or the absorbance is A. So this is a very explicit way of writing the emissivity. So a layer of the atmosphere which is absorbing radiation from the bottom, so to say, in the case of long wave terrestrial radiation, the atmosphere gets it from the lower side. That is expressible in terms of its density, in terms of the absorption coefficient. That means how much it has been able to absorb. So that is the rate at which it will emit also. Now, this is essentially what the Kirchhoff's law tells us. Why has it got stuck? Yeah. Now, we shall use this in trying to construct the transmission of radiation through the various layers of the atmosphere. consider this, that we are at the moment talking about the infrared radiation, which is also known as the terrestrial radiation. You can apply it for radiation coming from the top in the case of shortwave, but the principles have been given in this series of equations. That's all. Now, this layer, it receives a certain amount of radiance, and then it gives out a certain amount of radiance through emission. Now, this is the temperature of that layer, and it has properties of density and the absorption coefficient K lambda at the given frequency. For different frequencies, the K can be different. And for different frequencies, the Planck's law also says that the amount of radiation will be different coming from the black body Earth. All right, now this has got a delta S finite thickness. So this is the situation that we are in. Here we now look at the emission from this particular body, from this layer, and the absorption. Well, the absorption is very simple. It is what we have done in the Beer-Lambert law, that the amount of incremental absorption by this layer, which is causing this to be I plus delta I, that is equal to minus of this product. This is the Beer-Lambert law in differential form. We have done this in the past. What we now add is a very small physics addition to this. What this is emitting is dependent upon the Planck's function, okay, and the emissivity. Okay, so what this layer will emit will depend upon the Planck's function at the temperature T. Remember, the ground is at a different temperature, and this is at a different temperature. So the shape of B at a value of T is going to be different from the ground, what the ground emits. So the ground will emit at a different temperature. Now, applying Kirchhoff's law, this emissivity, as I told you in the last slide, can be expressed as this term. Okay, whatever is absorption, the absorptivity is equal to the emissivity by the Kirchhoff's law. So if it's a good absorber, it's a good emitter. As simple as that. So these two together, remember that the absorption depends upon the fraction of the incident radiance, and the emission depends upon the Planck's function at a temperature T, and the fraction that has been absorbed by this layer. So the next is algebraic addition of these two when you talk of the net effect, and therefore if you algebraically add them, you get what is known as the equation of radiative transfer. It's in principle very, very easy. The only thing is that this is a differential equation, the solution of which in real life is very, very cumbersome. Now, what we get here is nothing but simplified form of this. This plus this is the total radiative transfer. Now, if you look at this, this is one term, Planck's function, minus the radiance that is entering the medium, multiplied by rho into K. And rho into K we saw was called the optical path. Now, that is the rate at which the radiance is reducing or increasing. Now, intuitively, I mean, before I begin to even propose the integration of this, your job is to find out I at various levels, isn't it? At different point in S, what should be the value of I? That is the purpose to be able to theoretically predict what should be the radiance emerging out of any given layer, not just an infinitesimal layer, but any given finite layer. So that's my problem. And for that, I need to integrate this. Even before proposing to do that, let's just look at this left-hand side. If you see that the radiance is continuously, as it is moving through the depth of the atmosphere, is falling. Okay, it's reducing. Okay, so what is happening is the medium is obviously absorbing that extra energy. Now, when the medium is absorbing that extra energy, it's at a different temperature. It becomes at a different temperature. But so the ground is emitting at a particular temperature. The medium is also absorbing this, and when it is coming to an equilibrium with respect to all the layers above it and the ground below it. So when that equilibrium is reached, it has reached a certain temperature T. Now, obviously, there is a variation of T with height. Okay? And the heat content of each of these layers is different. And the indication of that is that there will be a reduction of radiance as it is moving outward. Same thing will happen for shortwave radiation when the arrows get reversed. And if the shortwave radiation is passing through with through the different successive layers by a little bit of diminution, then the shortwave radiation is being absorbed. But observational experience says that the atmosphere is almost transparent to the shortwave radiation coming downwards. And therefore, the flux really does not diminish as the radiation travels downwards. Whereas in the case of the long wave radiation, which is in a net effect moving upwards, you will find that whatever was the radiance here, a lesser amount of radiance is emerging from the top of the atmosphere. And that is also causing heat to be retained by the atmosphere and the temperature to be altered. Now, temperature is not only dependent on what the radiation absorption is taking place. Temperature in the real atmosphere is dependent on two types of energy transfers. One is radiation, in which the flux, as it reduces, it means that the temperatures are also higher than zero. That means they're at a finite temperature. When it is opposite in the short wave, and I have said that the transparency is very high of the short wave, it is only in the case of certain aerosols, with black carbon in it, that you will find that the radiation coming down from the sun towards the ground is also diminishing layer by layer. That is because the black carbon is able to absorb. Now, this absorption that we have seen here is a property of gases in the long wave, okay, like carbon dioxide, water vapor. That means they absorb in the long wave. They don't absorb much in the short wave. So for the radiation that is coming downwards, in case situations where you find absorption, it is not in the case of molecular absorption. It is predominantly in the case of particulate absorption, which is, as we have seen in Mies scattering theory, absorption is also one type of scattering where the refractive index is complex. Okay, the refractive index of the medium is complex. That kind of a scattering leads to absorption. We have seen this in our earlier lectures. So to sum it up, what we now get here is that for long wave, this radiative transfer equation will tell you that a higher amount of radiation starts from the ground, and what goes from the top of the atmosphere is a far lesser amount of radiation. And this difference in flux is the greenhouse forcing as we have seen earlier. Similarly, in the opposite case also, if radiation travels from the top to the bottom, as in daytime, the short waves, and there are absorbing particles in the atmosphere, which cause diminishing of the solar radiation as it is coming downwards, there also the atmosphere will be absorbing. Okay. Now, you must realize that this rho, this K, they can get altered by advection of moisture from time to time in a particular layer. Therefore, this balance temperature, or what we know as a lapse rate that has been created in the atmosphere as a sum total of the effect of radiation as well as convection. Okay, so the atmosphere is not just in radiation, radiative balance, but it is also in convective balance. The moment you have higher temperature at the bottom, why higher temperature at the bottom? Because the absorption capacity of the layers of the atmosphere at the bottom is more. You have higher density. Okay, so it absorbs more, and therefore it will attain a higher temperature. As you go higher up, because of the Earth's gravity, we know that the density of matter keeps on reducing, and therefore the amount that it will absorb also will keep on reducing, and hence the temperatures will drop. Now, once the drop in temperature crosses a certain value, the atmosphere will break into convection. Okay, the atmosphere will immediately break into convection, and therefore convection and radiation, they will establish a certain temperature profile. The two together will establish a certain temperature profile. It is not very obvious from the radiative transfer equation and given densities what the temperature profile would be. That is not so obvious. Reason being, the atmosphere will also go into another transport mechanism known as convection. And therefore, a total balance is achieved under RC equilibrium, radiative convective equilibrium. And that explains most of the natural phenomena. Okay, now having said this, two essential things that I've said is that down the path, the reduction of the radiance indicates that the atmosphere has absorbed the remaining part of the energy. And that layer by layer, when you reconstruct this, you can explicitly find out how much has been absorbed. Okay, this is the purpose of the radiative transfer equation. A little more clear when we integrate it. Well, right. Now, once it is integrated, it's not very easy to integrate that, as I told you. And it's a two-step integration. And we kind of take this geometrical definitions that I0 is at the ground. Okay. Therefore, I0 will be the Planck's function at the ground, and Is is at the top of a certain layer. Now, this is a certain finite layer. This need not be the end of the atmosphere. The atmosphere can be even much more than that. But for any given end of layer S, the flux is this. My job is to find out I for different values of S. Okay, and that will tell you what is the rate at which flux is moving out. This is also called flux divergence, which helps to tell how much energy a layer is gaining or how much energy a layer is losing. So for that, you need to know I lambda S1 and I lambda S2, the difference between that. That will tell you what is the flux divergence, whether it is positive or whether it is negative. Positive means the layer is cooling, negative means that the layer is warming. Okay, now this integration needs to be properly defined. So we have, say, from S dash to S, this has to be integrated. And that is, so to say, a layer over here is absorbing as well as radiating. Okay. Now let's see the meaning of this. This integration has been already done, and this being, as I told you, pretty tedious, we haven't gone through the steps of it. But let us try to explain this physically. Okay, this is the final result. It says that it is integral from 0 to S. It's integral from 0 to S. That means from ground till the top of the layer. This integration has to be done. And here it is a double integration. Okay, here it is a double integration. Look at it. This is to be integrated from ground to the top, whereas this integration is from S dash to S, S double dash to S. That means it is an intervening layer. And as this intervening layer goes from 0 to S, so many such layers stacked one on top of the other, how they will add up to the total radiance is coming from this term. Okay, this is a very, very cursory look at this equation. Now let's look at it in more detail. This is the original radiance that the ground is giving out. Okay, now obviously this is attenuated. This is the Beers-Lambert's law. That means that whatever the ground has emitted, the depth of the atmosphere up to S has absorbed, okay, and caused diminishing of radiance. So this is this is I into exponential of minus this, and minus how much is the optical depth, okay, minus the optical depth. Now this is nothing but the total attenuation of the ground emission. This is the ground emission, isn't it? And total attenuation by the depth of the atmosphere is this. So this is only the first term. This may be the major term, but this is just the first term. Clear? The ground is not the only emitter. Remember that. There are intermediate emitters at S dash dash. Every layer is an emitter. And remember, every layer has a different temperature. So T is a function of S dash dash. And the Planck's function has to be a function of the temperature of that S dash dash layer. Clear? Now, what does this say? Look, we have seen the Kirchhoff's law earlier, that the emissivity multiplied by the Planck's function is the real atmosphere emitting at the point S dash dash. Okay, at the point S dash dash, this is the real atmosphere's emission. It's the Planck's function multiplied by emissivity. Clear? Now this particular emission from that given layer is attenuated as it reaches S. As it reaches S is attenuated. So from S dash dash to S, the attenuation is given over here. All right. So this is what it essentially means, is that the ground, if there was no other absorbing layer, and it would have, if there was no other emitting layer, would have only performed as an absorber. Okay. So this is the Beers-Lambert's law, that the radiance is reduced by the optical depth as it passes through the body of the atmosphere. But there are other things to be added to that. Stage by stage, every layer performs like an emitter because it has absorbed something. Because it has absorbed something, and the Planck's law you apply, it becomes an emitter. But that emission is again attenuated by the remaining part of the atmosphere on top of it. All right. So, and that whole thing has to be integrated for all the layers from 0 to S. Okay. So ds dash dash has to be integrated for all the possible layers right till the top of S. So these are essentially the two major terms. One is the attenuation of the ground radiation, which is the major component, The other is all the intermediate layers emitting and that emission being attenuated down the line. Okay, so that is the sum total of the total amount of radiance emerging from S. So when you do S1 at one level and you do S2 at another level and find out the difference, you will be able to tell and monitor whether a particular layer is continuously gaining energy or losing energy. Okay, and please remember one thing, that this temperature T is not only connected to the radiative lapse rate, but it is also the net effect in the atmosphere, that of convection also. Yeah, and given the characteristic time of convection, we could say that the radiation balance establishes almost instantaneously. But the radiative convective balance has to wait for the lifetime of the convective phenomena. So if you are averaging over the lifetime of the convective phenomena, that is of the order of hours and days, you will find the atmosphere to be in radiative convective equilibrium. But the moment you go at the top of the atmosphere, you will find only radiative equilibrium because there is no convection there. So there it will be dictated only by radiative equilibrium. Now, the interesting thing is the density falls off with height continuously. Okay, so the contribution here also continuously falls with height. So the amount of emission that the atmosphere is giving is constantly reducing. So that at the top of the atmosphere, the radiation that is being emitted is substantially less. Now, if this rho were to increase, or for some reason K was to increase, sudden incursion of moisture or formation of cloud, okay, with sudden formation of moisture or sudden formation of cloud, this attenuation of the radiation would be far more severe on those particular moments. And as a result, you see, what we noticed is that when in the tropics there is severe convection, the outgoing radiation is reduced. So when the outgoing radiation is reduced for a given amount of I0, okay, for a given amount of I0. If the I0 changes for some reason, that's a different matter. But for the same amount of this, or if a particular moment you find that the radiation escaping from the top of the atmosphere has reduced, you know that it has been absorbed on the way. And severe convection is essentially that. What it does to the convective atmosphere is to warm up the atmosphere, okay, because release of latent heat. And so it changes the temperature profile. So all this happens within the lifetime of the convection. And so at the end of the convection, you will find that the amount of latent heat that has been released and the amount of latent heat that has been released is essentially because there was an incursion of moisture with very high values of this that has caused the atmosphere to behave like a bigger greenhouse, okay? Like a bigger greenhouse. The atmosphere is always a greenhouse, but in certain moments, it is a more intense greenhouse. And that is exactly, in other words, when you say that if the outgoing long wave radiation reduces drastically, it is the warming of the atmosphere that is taking place. And exactly opposite when the air is subsiding. Okay, in those areas of the globe where the air will subside, you will have very thin clouds at the top. Very, very thin clouds at the top. They will not be able to block the outgoing radiation. And so you will have a sizable amount of outgoing radiation when there is no convection, there is no advection of moisture into the column, when the absorbance does not increase. Okay. In fact, dry air in the subsiding air will cause the opposite effect. Rather than absorbing more, it will help to radiate more. Okay, and that's how the outgoing long wave radiation becomes so high in those areas which are cloud free. Now, this is a very obvious thing, and to understand that, you need not write in the integral form. You can simply argue it, but to write it in this integral form, layer by layer, you are able to do the integration. That is the most important thing. You can place the cloud at different layers and see what is the effect. When you write this radiative transfer equation explicitly in S, then you have this advantage that you can put this absorbing medium anywhere at different values of S and see what is its effect on the climate. All right, so that is the advantage. The other advantage of writing out explicitly in this integral form is that this is a method you are measuring using a satellite only, I lambda. Okay, at different temperatures, the different frequencies will be, the Wien's displacement law will give you different frequencies of radiation, okay, at different temperatures. So you have a method by which you can do the reverse way. You measure the radiances and infer what should be the temperature of the different layers, provided you know rho, you know K of all the intervening layers, provided you know that. If you don't know that, you cannot do this. So if you really know the composition of the atmosphere from ground to the top in terms of molecular components, scattering components, and so on and so forth, and also if you measure using a satellite, you have a way of finding out the vertical temperature profile. This is working the radiative transfer in the inverse mode. To solve for T. To solve for T is a very difficult problem, nevertheless, and does not result in unique solutions. And you have to reason out physically which of these solutions are acceptable. But nevertheless, the forward direction has only one solution. Only one type of flux can be obtained for a given combination of this. Okay, but the reverse, different set of temperatures can generate the same regime of fluxes. Okay, so when you work in the reverse direction, this particular equation, you can get more than one solutions which have to be filtered out using arguments. Okay, now that is the exact method by which satellites, they reconstruct temperature profile of the atmosphere. So this is therefore an extremely useful equation in its explicit form. In a differential form, it wasn't carrying so much of an information simply because the observable I was could not be found. Because you're using a differential of I. You're only seeing how I is getting attenuated. But to find I, its integral form is necessary. Well, did we kind of expect certain examples? One example is that we have seen that in an area of convection, where there's vertical motion, the flux is reduced drastically. The flux coming out of the atmosphere is reduced drastically. Now, what are the implications for, say, a greenhouse phenomenon? When the carbon dioxide is increasing in the atmosphere over a period of time, the lower parts of the atmosphere are getting warmer and warmer. And the upper parts of the atmosphere, they are losing more energy to the space, and therefore they're getting cooler and cooler. Okay? Therefore, a greenhouse phenomena automatically means, through this radiative transfer relationship, it automatically means that if the temperature near the ground were to increase, the temperatures above the near the tropopause would automatically decrease. All right. What it simply means is that as the atmosphere absorbs more and more, it leaves less to be given out to space, but then the radiation balance outside the atmosphere will be severely affected because the atmosphere has absorbed and removed some of the radiation that was supposed to go out. So what happens is the response is that the ground heats up. So the ground heats up and, so to say, starts with a higher value of outgoing radiation. In spite of the large amount of absorption that is taking place due to increasing carbon dioxide, the outgoing radiation is not affected because the ground has increased its temperature in response to the thermal equilibrium. Is that clear? If that be the case,
what it means is nothing but what we are noticing: surface temperatures increasing. Okay, and that is still maintaining the Earth in the radiative balance. So whatever the absorption is taking place here is compensated by a higher amount of radiation coming out from the ground. That means a higher amount of this radiation coming out from the ground. Clear? Right. Now, having interpreted very broadly this this kind of a situation, I would like to point out a little more how to deal with this. Is absorption. We are dealing with only absorption. And remember, scattering can be built into this term. Scattering can be built into this term when we write beta. Replace this by beta. You can add the beta of scattering to it. We have seen in the general form of the Beers-Lambert's law. But scattering will also change the function, because scattering is almost like emission. It is also giving out radiation in all directions, isn't it? Although not in an isotropic fashion like the black body would do, but in a highly anisotropic fashion. But nevertheless, in all directions, it is giving out radiation. So not only is the isotropic radiation there, but the scattering would add to a source function, so to say. The scattering always adds to a source function, so to say. So if you include scattering, it becomes much more complicated than the look of this equation. But there, the emission is not only the Planck's emission or the black body emission. The emission is also from the scattering medium. And therefore, mathematically, it is called equivalent of a source function, scattering source function. So you can define a scattering source function. And I just wanted to add this because even though we are not dealing explicitly with the scattering source function, but the fact that a scattering medium can also become a source, just like the black body is a source, but of a different nature, that has to be highlighted. That is important over here. Now, very quickly, let me take an example. This example shows that there is clouding in the lower levels, and here there's thin clouding in the upper levels. What our notions of radiative transfer, apply them, and let's see. As this cloud is lower down, its temperature is higher, it will have a higher amount of thermal emission, okay, long wave radiation. Okay, this being a deep cloud will also have a higher albedo, so it will send out more. And so what is available below the cloud is less. So this will cause a planetary cooling. Okay, so this will cause a planetary cooling. But a cloud which is much higher up, thin cloud which is much higher up, will reflect much less. Okay, will reflect much less. And because it is at a higher at a lower temperature, being at the higher up, its thermal radiation will also be much less. Planck's law would simply say that it would be much less. And therefore, most of the radiation is available below the cloud for this to become warmer. Okay, for this to become warmer. It doesn't attenuate much of this radiation, it passes through. Here there is a huge optical depth. So the radiation coming out here is much less. And therefore, there is a cooling effect. Now here, the optical depth of these clouds is not much. And so a large part of the radiation comes below that. Okay. And even though a large part is reflected, but nevertheless, the ground is at a higher temperature. And so a large amount of thermal radiation is there emitting from here. But emitting from the top is much less because this is at a much lower temperature. And therefore, what you have a situation is warming. So long-lived clouds at the higher levels versus the shorter-lived convective clouds at the lower levels with a much bigger depth have just the reverse effect in terms of climate. All right. Now, these are very basic elements that we can infer from the nature of the radiative transfer equation that you have seen. Okay, now you can apply your imagination. Like for instance, the subtropics is somewhere the tropical air rises and symmetrically distributes on either side of the globe and descends at the subtropics. Why it descends at the subtropics is that the air that rises above the tall tropical clouds, they are dry because all the moisture has been removed as rain. So that air will radiatively cool because its absorbance is less. It'll radiatively cool. So therefore, the air that spreads out on both sides begins to cool radiatively and becomes heavier and starts to descend. And that is how they descend over the subtropics. Now, you see the definition of the Hadley cell is essentially because of the radiation cooling, isn't it? Where the radiation cooling is enough for it to cause subsidence, there you have the subtropics. And so the taller the cloud, I mean, it's just for you to conjecture. This is a very strong conjecture. The taller the cloud, the drier will be the outflow, and the closer will be the subtropics to the equator. Now, this is a very fundamental problem, which is a distinct possibility in the future climate scenario, where the global warming causes clouds to become taller, and outflow becoming drier, and therefore the subtropics coming a little closer to the equator. Okay. Now, there are many ways in which you can look at the radiation balance and how you can interpret the radiative transfer process. Having said that very quickly, I will now, I promised you a minute or so for the observational things. All right, now look at the nature of diffuse radiation. It is scattered radiation, okay? Now this is along the Earth-Sun line. Forward scattering, I told you, is high. And light that is reaching here is coming to you after a 90-degree bend, a 90-degree scattering angle, where it is scattering intensity is much less. It is scattered much less in the perpendicular direction. So if you're looking at the sky, you will find along the sun on either side, you will find a lot of scattered radiation, and perpendicular to it, a lot of less amount of radiation. Now, this is the nature of the diffuse radiation. This is the very nature of the diffuse radiation because of scattering. And this nature alters when the scattering properties change. When the forward scattering to perpendicular scattering ratio increases, like in B scattering, this becomes much more prominent than what we have seen in this diagram. All right. And therefore, around the sun, you see a distinct haze, and perpendicular to the sun's direction, you see completely dark blue sky. Okay. Now, this is how your daily experience can be explained. Now, this diagram that I've drawn here is pretty obvious, which is again using scattering here as Rayleigh scattering along the path. And this is me scattering due to the aerosol from the sun forward direction. It is scattering much more. So this lobe, you will find scattering much more. So you oscillate between this on some of the clean days to some of the dirty days to this kind of a scattering regime. Now, instruments that measure the sun directly, as I told you earlier also, is known as the pyrheliometer. It looks at the sun. It's a collimator that looks at the sun. But then this looks at the sun plus the forward scattering from the limb of the sun. Okay, plus a lot of forward scattering from the limb of the sun. So not at all good for finding out the solar radiation, monitoring the solar radiation coming from the sun. That is one thing. The second thing is direct radiation. In addition to that, you have radiation coming scattered from all directions. And therefore, this sensor is different from a telescopic sensor. Okay. This sensor is exposed a glass dome on all sides. So it gets radiation from all the directions. So it gets both the direct radiation as well as the diffuse radiation. And this instrument is called pyranometer. And this is called pyrheliometer. Pyr means warmth or temperature. And then pyrheliometer is that of the sun. So you're measuring the temperatures of the sun, so to say. Pyrheliometer and then pyranometer. These are two classes of equipments. When you have global exposure,
or hemispheric exposure, you call it a pyranometer. When you have an angular exposure of the dimension of the sun, you call it a pyrheliometer. Now, pyrgeometer is when you don't use glass, but you use some other substance that cuts off the short wave radiation and gives only the long wave radiation. So geometer is the terrestrial radiation. It is only allowing the long wave radiation to pass through 4.5 to. That's how the kind of filter that you use in this glass. That's all. And a pyrradiometer is a combination of the long wave and short wave. Okay, this is a short wave and this is a long wave instrument. When you see the net radiation as a sum total of these two, you call that as a pyrradiometer. So 3 classes of equipment, 4 classes: pyrheliometer, pyranometer, pyrgeometer, and then pyrradiometer. And their purposes also have been given here. The other thing that somebody had asked me this question, and that's why I have included it here, is that sun photometers are a little more sophisticated than pyrheliometers. It looks at only the limb of the sun and not only at the disk of the sun and not at the limbs. Okay, it looks something like this, and it can track the sun wherever the sun is going. It has a servo motor. It can track it. Okay, so you can have these observations continuously running throughout the day, and at what angle you will get the sun is very easy to get astronomically. For a given latitude, given day of the year, you know at what time, local time, where the sun is to be found. So you can easily focus it at the sun, and using a device, you can always lock into the sun and continuously track it. Now here, the Beer's law can be verified using this. Okay, this is a voltage. It looks like the Beer's law in terms of voltage that is being measured in a detector over here. That's all. What is this? E to the power minus m. M is the path length, integral ds, but corrected for the refraction. So it's not just that the angle 1 upon sec theta, not just that. This path is not just 1 upon cos theta, but it is also a refracted path. So it will be slightly more than that. So m is slightly more than 1 upon cos theta. And that correction can be applied depending upon the time of the day. Okay. This correction is normally known as the air mass. So when you correct for the air mass and you find out the optical depth, you find out the optical depth of the atmosphere. And this, if you remove the optical depth due to aerosols, due to air molecules, you remain with the optical depth due to aerosols. They're all additive, isn't it? They're all additive. So when you remove that due to molecules, what you get is the remaining part is that due to aerosols. So the Beer's law has been applied here to find out the aerosol optical depth. This is the purpose of a sun photometer. Okay, there are very complicated sun photometers which give you many more things by not only looking at the sun, but also looking at the sky at different angles. And that gives you a wealth of information, not only on the optical depth, but also on the scattering properties. How much of refractive index is real and how much of the refractive index is imaginary. From there, you can find out how much is the absorption by the aerosol and how much is the scattering by the aerosol. So there can be more complicated instruments using the sun photometric mode known as the sky radiometer. That is called a sky radiometer because it looks at not only the sun, but also at the sky. Now, it uses simply the Beer's law predominantly to get what is the optical depth in terms of the voltage that you have measured. This is the voltage at the, if the instrument was to be kept outside the atmosphere. All right. There are ways of calibrating this. You don't need to send the instrument at the top of the atmosphere. There are ways to calibrate this. Well, that brings us to the end of this lecture. And what we have achieved I will just go in very short in this entire 4 lecture series, is that we have tried to create the kind of a scenario in which the atmospheric radiation can be modeled. Okay, the emissions, the scatterings, the absorption, all of them was modeled separately. And not only they were modeled separately, but they were also added into one equation giving you the transmission through the atmosphere. And well, the applications of that we have discussed. In the forward direction, you can find out the fluxes. In the backward direction, used that same equation can help you to retrieve the vertical variations of the atmospheric temperatures. So that brings us to the end of this lecture. And I must thank all of you. I'm sure there will be a lot of questions. Please, I'm willing to answer them.
Dr. Rohini, can you take up the questions?
Yeah,
I will. So the first question is from Pramod Kumar. He wants to ask, is radiation of tropospheric layer more variant than other layer, and other layer behave constant radiative body?
Well, let me try to understand this question. You probably want to know that the variation of radiation of the fluxes in the troposphere, is it more than that in the other parts of the? Yes, that is true, because the composition varies in the troposphere. As a result, the absorption rates, the scattering rates, they all change from time to time. But if you go into the stratosphere and into the mesosphere, the composition is relatively stable. Okay.
Another question. Thanks for the wonderful lecture and simplifying the radiative transfer model. Sir, can we calculate layer-wise AOD, like extinction coefficient, at each pressure level like temperature? That is the first question. Is it okay to integrate the tau within each kilometer of vertical profile? Anonymous person.
Yeah, the method of finding out the vertical variation of tau. Tau is an actually integrated property of the atmosphere, right? You don't really talk about the in situ value of tau. Like you have absorption in situ. That means in a closed volume in the atmosphere at a certain height, what will be the absorptivity? You can define that. But optical depth is the integrated effect. And therefore, you're really not looking at vertical variation of optical depth. But yes, you're looking at the vertical variation of scattering coefficient. That is something you're looking at. And the way that, how to find that is to use a laser beam and to use it in a bistatic mode. That means one emitting and one receiving. And you can change this angle and you can target different layers of the atmosphere. And from there, you can, from the backscatter coefficient, you can find out the number of scattering particles at different layers.
So another, I think two to three participants have asked the same question. What solarimeter equipment measure?
I'm sorry, I didn't get the question, please.
What solarimeter equipment measures?
What solarimeter?
Yeah.
So what is the real question?
What it measures?
What it measures?
Yeah.
Well, what is a solarimeter? We use with the measuring instruments that I have said, but I am not too sure what's the solarimeter. Is it a standard term? Solarimeter could be the sun's radiation coming out in some integral form. Yeah, it's basically a sun photometer.
Okay. There is one question by Dr. Kitri Bhatta. They have asked, what is the cost of the radiation sensors of all the instruments? And if we want to build a lab, how much it would cost?
It depends upon what you want to measure and how sensitive. How sensitive. Yes. What kind of a and what kind of a device you are there for doing the detection? A photomultiplier tube or a selenium solid state device?
depends upon at what temperature you have to keep it. So the cost depends upon how cumbersome the equipment is. And that also depends upon how much of noise you want to cut down in your measurement. Okay. You can use a solid state device with a little bit of noise, and so your detection limit will be a little high. But if you really want to cut down the electronic noise and you go to PM devices, photomultiplier tube devices, you have to keep it cold. And so the temperature goes up as a result of that. I wouldn't be able to give you the exact value of the costs, but I have told you on what would it depend.
There is another question which says, please can you explain more the influence of the desert on scattering radiation?
One sec. You see, I have a little bit of audibility problem on my machine. You would mind asking that question again a little louder?
Yeah. Yes. So they have asked, please can you explain more the influence of the desert on scattering radiation?
Oh, what is the influence of the desert? Okay, we have discussed this one day. The deserts would have more reflectance, okay? And so to say, the albedo is higher. And so more light will be reflected and less light will be available, sunlight will be available to the ground for heating. A consequence of that is that Charney's famous theory that it will result in, if the atmosphere is not getting heated from the bottom, it would like to get heated by subsidence, by adiabatic compression. And so that's the natural consequence. And over the deserts, the climate effect is that of subsidence, simply because the atmosphere is not getting the heat from the ground because of the higher albedo of the desert soil.
Can we measure temperature at different levels using SODAR, a single cup antenna?
At different levels of SODAR? Well, let me try to recall, because SODAR is not directly related to EM waves. It's related to mechanical waves, compression. What does it depend on? Reflectivity, density variations, turbulence. This is something which is required for detection using a SODAR. And vertical variation of that coming from the temperature, well, I have to manufacture an answer for you. Yes, the density is the method by which you can find out the temperature variations in the SODAR as well. Okay.
RAS measures temperature, but does the same done by SODAR?
No, so RAS measures the temperature by change of refractive index, but SODAR does not measure vertical variation of temperature on its own. But RAS combined with a SODAR synchronized with the electromagnetic pulse, the sound pulse and the electromagnetic pulse, they are much more powerful. Yes, they will give you the density profile and the temperature profile. Yeah.
Yeah, I think that was the last question.
Well, the acoustic waves was not a part of this because it's not an electromagnetic wave. So maybe my answer is a very general answer that I gave you.
Yeah, that was the last question, sir. So,
oh, was that the last question? Okay.
Only there was one more question from YouTube. Mohan posted.
oh,
Yes, please.
Very interesting question. You can take it.
Yeah, one more from you. What is the importance of the plane parallel approximation in atmospheric radiative transfer?
What is the importance? You see, I'm not a computational radiative transfer person. I'm not the best person to answer this. Yes, there are obviously advantages of a plane wave treatment. Less of diffraction problems and issues like that. But I'm not the best person to answer this question.
Thank you, sir.
Okay.
To you, Dr. Lakshmi.
Yeah, thank you, Dr. Rohini. So with this, we have come to the end of this third module also. There is an atmospheric radiation. So on behalf of SAMA and SRM-IST, I thank Mukhopadhyay sir for giving this lecture on radiative transfer, which is very, very, very much interesting talk, especially those who are working in aerosols. So now I request Dr. Mohan to propose the vote of thanks.
Thank you, Lakshmiji. I think before my vote of thanks, as this is the last lecture, so maybe we can request Dr. Someshwar Dutt sir to say a few words.
Well, certainly we would like to thank Dr. Mukhopadhyay very much for all these 4 lectures. In fact, he has delivered a very complex subject of radiation into a very simple way. I mean, I don't think I can't imagine a simpler way of explaining the atmospheric radiation than what Dr. Mukhopadhyay has done in the last 4 lectures. So I should say that all the audience, all the participants, you are really, really lucky to have heard the atmospheric radiation, the basic concept. In fact, it is just a basic concept he has done in 4 lectures. Otherwise, atmospheric radiation is a very vast subject. And as you know, I mean, there are books, full textbooks written on this, which is a full semester course of 6 months or even more. And that has been kind of a, squeezed into just 4 lectures. And in those 4 lectures, he has almost covered almost from fundamentals to the, complex things like this radiative transfer. The radiative transfer, its equations are very complex equations. And as he has said that, it requires a lot of computational ability to compute those layer by layer, the influxes and outward fluxes, upcoming and ongoing radiations, etc. So it's a very complex subject. And somebody was asking what is plane parallel, what is the use of plane parallel approximation? The simple way of saying that it is simplifying a very complex radiative transfer into a very simple way with assumptions that the sun's rays comes down in a very straight line form in a parallel way. So a very simple way to explaining that. But otherwise, if you just take up the entire solar radiation spectrum, then it will be very, very complex and horrendous to handle in the equations, in the numerical models. So he has, in fact, explained to you in very simple terms. And I would like to really thank Dr. Mukhopadhyay once again very much from the bottom of my heart. And I definitely expect to hear from him again in future, because this kind of lecture series will continue now in future also. So let's thank once again Dr. Mukhopadhyay. A big clap to him, a big hand to him. And this is the end of the 3rd module. And the next module, the last module, will be on cloud physics, which will start next Saturday by Professor Pradeep Kumar from University of Pune, Department of Atmospheric Science. And Professor Pradeep Kumar will again, kind of condense not the water vapor into small particles, but condense the entire cloud physics subject into very small part, so that you can understand and grasp in just 4 lectures. Only 4 lectures we are again allowing for the cloud physics, which again, there are volumes and volumes written on cloud physics. Books are available for that, and it's a full semester course or even more than that. But you will hear from him. He's expert on cloud physics from next Saturday onwards. The 4 selected lectures on cloud physics, starting from fundamental to cover more or less whatever is required for general people to understand and utilization applications. There will be some kind of rescheduling of the lectures of Professor Pradeep Kumar, because there are some holidays during his lecture series, which we did not realize in the beginning while scheduling the lecture. Like I think there will be a Eid festival during his lecture, because his lecture will span for the whole month of April, starting from 1st of April to almost the 4th week of April. So during that period, there will be one festival, Eid, for which many of you probably would like to have a holiday. So that lecture will be rescheduled probably on the coming Monday. The next Monday of that lecture will be it will be scheduled on that day. And probably one more holiday I'm not able to recall. But
Vishu, sir. April 8th, I think. April 8th.
April 8th, Vishu. Okay.
Yeah.
So that will be another holiday. That will be also announced. Will be all announced properly in advance. So that will be shipped in the lecture schedule for those 2 holidays. And as I said, already will be, I mean, the lectures will be just rescheduled to the next Monday on that week. So this is the announcement, small announcement, and so that's it. And from my side, and we appreciate the questions and the nice way of explanation, answers to the questions which people have raised, from various, I mean, from the layman angle to somebody who probably has already a background of radiation, and the questions were kind of ranging like that. But he has answered very well on all the questions. So thank you very much once again, Dr. Mukhopadhyay, and we would certainly like to see you once again. Thank you. Yeah, Mohan.
Thank you, sir, for your nice words and practical information, which will help the participants for their to join the next lecture. So now this is time for vote of thanks. Respected resource persons, distinguished guest, esteemed member of the coordination committee, and dear participants. It is my honor and pleasure to express my sincere gratitude for the successful completion of today's international lecture series session on atmospheric radiation, transmission through the atmosphere. This is the last part of the lecture. I would like to extend my heartfelt thanks to our esteemed speaker, Dr. B. Mukhopadhyay, former Additional Director General of Meteorology, India Meteorological Department, Pune, India. Your informative and enlightening speech has left an indelible impression on us, and we are grateful for your invaluable knowledge and expertise that you have shared with us. I am confident that your presentation has provided us with a new perspective on atmospheric physics and has inspired us to pursue further research in this field. I also want to express my sincere appreciation to the respected member of the Coordination Committee of SAMA's training course, including Air Vice Marshal retired Professor Dr. Ajit Tyagi, President of SAMA, Professor Dr. Someshwar Das, Secretary of SAMA, Dr. T.V. Lakshmi Kumar, SRM IST and Session Moderator, Dr. Rohini Bhawar, SPPU India, Dr. Swagata Paira from BIT Mishra India, and Board of Directors and Organizing Committee for their tireless efforts and in organizing this highly effective training program. Your dedication and hard work have made this program a resounding success. Last but not least, I would like to express my gratitude to all participants from SAMA member countries and beyond for your enthusiastic participation and engagement throughout the program. Your active involvement has contributed significantly to the success of this event. I hope all of you will continue your participation and share your knowledge in the future. Once again, I extend my sincere gratitude to all of you and thank you very much. Thank you, sir.
Thank you, sir, and thank you all the participants. So next week we'll be meeting as usual, but with different module on cloud physics. I request all the participants to attend the talks. Thank you very much.
Photo session over.
Thank you.
You're taking the photos?
Sir.
Photo. Group photo, screen.
I think in the beginning we have
group
taken,
photo.
sir. We have
Okay.
taken in the beginning.
Only the Lakshmi's photo is not available. Lakshmi, you can switch on your video if possible.
I'm in mobile. That is what I'm.
Oh,
Yeah, just 1 second.
That's a minute. Yeah, so now perfect. Just a minute. I just make it full screen. So done.
Good. So very good. So
Thank you.
people are there. I see that today I think maximum 130 participants. I am correct. 130 participants were there. Of course, there were many more registrations. I mean, as announced earlier, more than 2,000 people registered from more than 48 countries. But still, I mean, 100, even exceeding 100 also is a good number. I just imagine if it was a real classroom, kind of an on-site classroom.
Yeah. So please realize this is 12th lecture we are organizing.
Yeah.
I think this was a real wonderful gesture from SAMA, and people have responded also very well.
Oh, yeah. And in fact, for many of you, the participants who are still there, From first week of next month, April, we are going to again start a training on NWP, WRF modeling system.
Sir, Lakshmiji, could you please stop the live of YouTube?
Actually, I can't do it. I have to end the program, I think. One second.
I think who is the host? Host can do it.
No, I am the host. I'm just finding
Oh, you are
out
the host. Yeah.
where I can
Okay,
start.
sir. Dr. Somashwar sir, you can continue.
Yeah, so I was saying that from 3rd of April, we are going to start this training on WRF modeling system. And this is going to be a very unique training because training on a model,